Hello everyone. Am I audible?
Yes, sir.
Okay. So let's start where we left in the last class. We were discussing the types of relation, right? And we have discussed about the three types of relation: reflexive, symmetric, and transitive. And we have seen that if we can form the relation, then we can easily identify. We have different methods to identify how when will the relation be a reflexive and symmetric, similarly transitive, right? And if a relation follows all three properties, that is reflexive, symmetric, and transitive, then we can call that relation as equivalence relation, right? That's what we have discussed. Now let's solve some more questions on this because see, there is one more variety of the question. One variety is that you will be given a set, right? And some relation. So you'll be having values and you'll be able to form the relation, create the relation, right? Now, in some cases, you will not be provided, I mean, you cannot visualize this. Like here you have pairs 1, 1, 1, 2, 2, 2. In the last question we were solving, this was the relation, right? So here we do have all the pairs to check this, right? But in some problems, the problem will be theoretical. So you won't be able to get these paired values, right? So let's solve 2, 3 questions. So yes, we were discussing this question. So can you answer this, whether this is reflexive, symmetric, or transitive or not? So this is clearly reflexive, right? Because this relation is forming on the set A, 1, 2, 3. It consists 1, 2, 3, 4, 5, 6. So we can call this relation reflexive if it consists 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, right? It do contain all the pairs 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So hence this relation will be reflexive. Now let's comment on symmetricity and transitivity. That I'm interested in to know from you guys. And we know that we don't need to check these 6 pairs now, right? They will follow all the properties. I mean, simultaneously. They will be reflexive as well as symmetric as well as transitive. They won't create an issue. So you need to check other pairs now. If 1, 2 is there, 2, 1 has to be there. So is it symmetric?
No, sir.
No, right? Okay, Austin. Yeah, correct. It is not symmetric. Now, let's talk about transitivity now. So if 1, 2 is there, then we will check whether, so how we can start doing it. We'll also learn, we'll also learn a new perspective today, how to check this directly, right? For the same question. Without forming the relation, how could I have checked that whether the relation is reflexive, symmetric, or transitive? So, but to check mathematically, like if you want to be really sure, this is a good method that you can take a pair and then search for the pairs which can be transitive with this. To know that, I have to take all the pairs from this set which starts from 2, right? Because it is ending on 2. So let's take all the pairs. So this is one pair, 2, 4, 2, 6, right? So we have 2 pairs which starts from 2, 1, 2. For 1, 2, we will check for 2, 4 and 2, 6. So if we check 1, 2 and 2, 4, then we should have 1, 4. And for this, we should have 1, 6. I think both are present. 1, 4 is here. And 1, 6 is here. So the given relation is transitive for 1, 2. Now let's come for 1, 3. So take all the pairs which starts from 3. They are 3, 3 and 3, 6. You can find them out. There are 2 pairs which starts from 3, right? So for this, I don't need to check, but 1,3 should be there, right? Oh, we left 2,2 here, but obviously we don't need to check 2,2 because with 2,2 we need 1,2. It starts from 1 and ends at 2. So 1,2, which is already present. This is the pair we are comparing, right? So we don't need to check for 3,3 as well. But if you check, you get 1,3, which is already present. For 3,6, 1,6 should be there, which is already present. Similarly, 1,4, 1,4 we have 4,4. It will be transitive, no issues. Then we don't have any other pair which starts from 4. So this is also done. Now let's come to 2,4. 2,4 is 4,4, already done. I mean, we don't need to check for 2,4 and 4,4 combination. Then 1,5. 1,5 is 5,5. This is already transitive, right? Guys, you're getting this. Did you? I mean, if you're facing a problem, please speak up. Feel free to ask. Then if we get 1,6, we only have 6,6. 2,6 also 6,6. 3,6 also 6,6. So all of 3 pairs will be transitive. Hence, we can say that the given relation is reflexive and transitive, but not symmetric.
Sir, can you just explain once more how did you do the transitive part?
Yes, Shaviz. We'll first discuss it. I mean, this is mathematical approach. How can you go for it? So you just have to take a pair. Don't take those pairs which are reflexive, like 1,1, 2,2, 3,3, 4,4, 5,5, 6,6. Even if the relation was not reflexive, what do I mean by that? Let's say we don't have all the 6 pairs. We have only 5 pairs. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Now the relation is not reflexive, right? But still, we won't check for these pairs because they will always satisfy the conditions of symmetricity and transitivity, right? So what I mean is that don't take pairs which are reflexive in nature. Okay. Then for transitive, take a pair, or I mean, leave all these 6 pairs. Then we will start with 1,2. So for 1,2, if we want to check that 1,2 is following the transitivity or not, then we will take all the pairs which starts from 2. Right? Because the rule was a comma b. If you have a comma b and b comma c, if you have a comma b and b comma c, then a comma c should be there. Then only the given relation follows transitivity. Right? So for 1,2, I'll take all the pairs which starts from 2. First is 2,2 that I'm leaving because I know that this will certainly follow the transitive property. And how you can check this here? Because 1,2 and 2,2 should give you 1,2. But you were already checking for 1,2, no? So you have 1,2 in the set. So that is why we don't need to check for these. But for the other pairs, there are 2 more pairs which starts from 2, 2,4 and 2,6. So for 1,2 and 2,4, if 1,2 and 2,4 is there, then 1,4 should also be there, which is present, right? And then we come to 2,6, then 1, 2, 2, 6 will form 1,6, and 1,6 is also there. Similarly, we do this for all the pairs. Did you get it, Shavis?
Yes, sir.
Okay. Now there is another perspective to the question. You can solve the question without even writing the relation. How? Now understand the understand what is reflexive symmetricity and transitivity showing to you. The nature of reflexive. So the nature of reflexive says that x and y both should be same, right? Means that x and y has to be same. So you put in place of y, you put x and see if x comma x is satisfying this criteria, whatever we are saying. So in this relation, we had the rule that we have to form the relation with the rule y is divisible by x. only x comma y will be there in which y is divisible by x. So you replace y with x, then you get the rule x is divisible by x. Is it true? Yes, x is divisible by x. Every number is divisible by itself. Hence the rule is true. That is why the relation is reflexive. That is why you got all the pairs 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So in place of y, replace with x and try to check that rule according to the reflexivity condition. I mean, reflexivity condition says that replace y with x. I need x comma x pair, all the x comma x pairs which are present in the set on which you are forming a relation, right? So in this, if you replace y with x, then you are trying to check for reflexivity and then see if that rule holds if you replace y with x. So here the rule was y is divisible by x. That was the rule defined for the relation. Now we are replacing y with x. So x is divisible by x. Yes, that is true. If that is true, the given relation is reflexive. Now, why it is not symmetric? Understand it. So for symmetric, we will have to take y, x comma y first. Then if x comma y is there, then y comma x has to be there, right? That was the rule. So here, if y is divisible by x, is it certain that x must be divisible by y? See, if you are writing the relation x comma y, then you are saying that y is divisible by x. For symmetric part, you need all these pairs too. If x comma y is there, then y comma x should be there. Now, y comma x should be there, mane? What does it mean? That x must be divisible by y. Then only we can form this, right? Now, you have to check whether it is true or not. If y is divisible by x, then in all the cases, x must be divisible by y as well. Is it true?
Yes, sir.
Okay. So you are saying that if 2 divides 6, then 6 also divides 2. No, right? It is not, I mean, it is not necessary that if, in fact, not necessary, क्या बोले मतलब कुछ ही केसेस में ऐसा हो पाएगा. I mean, there are very few cases माने you have to take the same value 4,4. Then only it is true that if y is divisible by x, then x must be divisible by y. Otherwise, it won't be true. If 2,6 is there, then 6,2 won't be there. Why? Because 2 divides 6, but 6 does not divide 2. So for symmetricity, what we are saying is that if x comma y is there, then y comma x, if x comma y is present in the relation, then y comma x must also be present in the relation, which is not true. Why? Because the rule says y is divisible by x, then we have x comma y. But it is not possible that x is also divisible by y every time. Chavez, did you get it?
Yes, sir.
Yeah.
Sir, both of them should be divisible, like.
Yes, I mean this condition will change with every question. There may be another condition, but to check this, to check symmetricity, we have to think like this: that if x comma y is there, then y comma x has to be there. So if there is some other rule written here instead of y is divisible by x, then we have to apply the same condition for that rule. तो rule change हो सकता है. Austin, I'm not saying anything new. So rule change हो सकता है. The rule can change that relation is forming on y is divisible by x right now. It can be anything else in the next case. But if you're saying that, but to check symmetricity, you just have to apply the same rule on y comma x as well. Whatever is true for x comma y, will that be true for y comma x? That is how we will be checking all the questions. Got it?
Yes, sir.
Okay. Now let's check transitivity also. So transitivity says that if x comma y and y comma z are present in the solution, right? Then x comma z should also be present in the solution. Now let's think about this. X comma y will be present, mane? It means that y is divisible by x. And y comma z is present, it means that z is divisible by y. The second value is if the second value is divisible by first value, then that is a pair of this relation, right? So if x comma y is present, it means that y is divisible by x. If y comma z is present, then z is divisible by y, right? It says that if x comma y and y comma z is there, then x comma z has to be there. Now, what does x comma z means? That z must be divisible by x. Now, sometimes it can be, I mean, it can be cumbersome or it can be difficult to visualize these things, but with practice, you'll understand, or you can take examples for your help, right? For your reasoning. So you can take here an example that if x divides y, so let's say 1 comma 3, or let's say 2 comma 4. Okay. So 2 comma 4 is a pair. Why? Because 2 is dividing 4, or 4 is divisible by 2. And then we are taking another pair which starts from 4, means that we have to find some number which is divisible by 4. So 4 comma 8, let's take 4 comma 8. Okay. So 2 is dividing 4, or 4 is divisible by 2, and 8 is also 8 is divisible by 4 here. Both pair says that 2 comma 8 should be present in the solution if this is the case, right? Which is true. If x divides y and y divides something else, then x must divide that thing, because x can already divide y. If y is divisible by x, then any number which is a multiple of y will be divisible by x. Or you can think like that if 4 is divisible by 2, then every number which is divisible by 4 will also be divided by 2, right? Or if 3 divides something, let's say 9 or 12, then all the multiples of 12 will be divided by 3, right? So that is why the given relation is transitive.
So I can just say once again.
Yeah. So if x divides y and y divides z, then x must also divide z. Like, you think it like that x is a divisor of y. So if let's take an example. So 3 comma 6. So if 3 is dividing 6 and you find another number which is divisible by 6, then you already know that the number is divisible by 3 also, because 6 has two factors, 3 and 2. So all the numbers which are divisible by 3 and 2 will be divided by 6. And or conversely, you can say that all the numbers which are divided by 6 will also be divisible by 3 and 2. So what we are saying is that if x is a divisor of y and y is divisor of something else, then x is also the divisor of that thing, because x already divides y. तो y से अगर आप किसी को भी डिवाइड करोगे तो वो x डिवाइड उसको करेगा ही करेगा. लेट्स से 3 6 वाला एग्जांपल मैं इसीलिए दे रहा था कि 3 अगर 6 को डिवाइड कर रहा है तो 6 तो सभी को डिवाइड, और 6 से जो भी नंबर डिवाइड होगा वो तो 3 से डिवाइड होगा ही होगा अभी, राइट? So that is what we are saying, that if x divides y and y divides some other number, then x तो will definitely divide that number, because it's a small unit of y only. No?
Yes, sir.
Okay. Now let's discuss some more questions on this, because these questions are tricky and I know that you will face problems in some of the questions. So, but let's finish this part today, relations, and then we'll
So can I
start
just
with
go ahead?
function. Yeah, please.
Can I just go ahead?
Acha, oh, sorry. I thought you were going to ask a problem. X must be a divisor of that. Please open everyone. Please open your NCRT.
Yes, sir.
Okay. Come to page number 5 and let's solve this first question, fourth part. So there is a relation given, relation R in the set Z. So the name of the relation is R, relation R in the set Z. Do you know what is the set Z? This set of integers. So we have some standard sets. Z is a symbol of set of integers. Remember this. This will be used. Okay, so we have a relation R in set Z, that is set of integers. And this is not a small z, so I should remove this. Defined as, now what's the rule of the relation says? R is the relation in which the condition is x comma y is a pair of R if they satisfy this. If their difference is an integer. Relation R in set Z, that is set of integers, is defined as the relation consists all the x comma y where x minus y is an integer, and obviously x comma y are from where? From this set, right? Because we are forming the relation on this set Z. Now what is Z? Z is the set of integers. How many elements are in Z? Can you tell me? फटाफट बताओ, कुछ कुछ ये तो हल्के हल्के क्वेश्चंस पूछ रहे हैं. These are easy questions, then we will be able to make a better understanding.
Minus infinity to infinity.
Minus infinity to plus infinity, so infinite elements, right? There are infinite elements present in the set Z. Now if you want to form this relation, so you won't be able to solve the, I mean, you won't be able to write the whole relation. You can only understand it. You won't be able to write it. You can write 2, 3, 4, 5, 6 pairs, but you have to understand how these pairs are forming. So pairs are forming that if x minus y is an integer, right? Now if x minus y is an integer and x and y both are integers because they are coming from set Z, capital Z, which is a set of integer, right? So will x minus y is an integer, this relation follows reflexivity, symmetricity, and transitivity. Now let's check it out with me. So first I'll check it for reflexive. So first thing I wanted all of you to understand that there are some cases in which you won't be able to write the whole relation like this, but still you can solve some pairs. You can write some pairs, but there will be cases where you won't be able to write a single pair. Okay, you just have to visualize it. You just have to think through it, like what is happening, what is the rule of the relation saying. So in this case we can easily form some rule, I mean some pairs. So I'll try to solve it for you. You can take any integer first of all. Understand this, that if you take an integer as x and then another integer as y, because x and y both have to be integers if they are coming from this set, which is a set of integers. So then they can take any value which is integral. So can be negative, can be positive, or 0, right? 0 is also an integer. So minus infinity to plus infinity, they can take any value and their difference would always be an integer only. No? So if you take 1 and you take any value for y, and you say that y is an integer, but I'm taking 4, 5, 6, 7, whatever you take,
Sir,
every value. Yes.
0 is an integer.
Yeah. Neutral integer, positive, negative, and neutral.
Okay.
So if you take any value and any integer in place of y, the answer will be an integer only. 1 minus 2 is also an integer because it comes minus 1. And 1 minus 0 is also an integer because it comes 1. Then 4 minus 3 is also an integer. Whatever you take, if you take the difference of two integers, this is always going to be an integer only, right? So in this case, you don't have to write actually any pair. You can understand it from here only. But for your help, I'm just writing some of the pairs. 1, 1 will be a pair of this or not? Can you tell me? If
Yes,
you
sir.
put is right, if you put 1 as x and 1 as y, then 1 minus 1 is 0, which is an integer, right? So 1, 1 is there. Then 1, 2 will also be there. And similarly, there will be so many answers. This will be an infinite set, right? But to understand it, now this is one way. Now let's check it from the perspective we have just discussed. For reflexive, what I will do is I will replace y with x, right? Replace y with x in the given rule. So if I replace y with x here, then x minus x comes out as 0. So you can start solving it like this. First replace y with x, then after replacing y with x in the given rule, when you come to this statement of the rule, put a question mark. If the answer of that question mark is yes, then your relation is reflexive. If the answer of that question is no, then your relation is not reflexive. So in this case, the question is x minus x is an integer. I mean, just change the this is grammatically wrong right now, but what you do understand it, right? That x minus we are asking that if x minus x is an integer or not. So is it true? X minus x, what will you get? 0, right? 0 is an integer. So if the answer is yes, then the relation is reflexive. Or in simpler words, in mathematical words, what you are saying is that you can take all the pairs because their difference 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, minus, minus 1, minus 1, minus 10, minus 10, minus 100, minus 100, 0, 0. You can take all these pairs because their difference is 0 only. So their difference will always be an integer, right? For symmetricity, you first check the rule for x comma y, whether x comma y is true or not. I mean, no, sorry. The x comma y wala rule, you will consider that rule to be true, right? Because we check it like this: if x comma y is present, if x comma y, then y comma x should be there. So in this, what we are discussing is, you can understand it like this: if x comma y holds, if x comma y holds for the rule, so consider it a true statement for x comma y. So you have to check if x comma y is satisfying the given condition. It means that x minus y is an integer, right? So we are taking x comma y to be true. It means that whatever x and whatever y we took, x comma y is an integer. Sorry, x minus y is an integer, right? So if x minus y is an integer, then y minus x is also an integer. So for y comma x, you will write this condition as, you will replace the role of y and x and y, interchange the role of x and y. So in place of x, you have y now, and in place of y, you have x now. So this changes to y minus x, this expression, right? So if x minus y is an integer, then will y minus x be an integer or not? Take an example for your help. If 2 minus 4 is an integer, then 4 minus 2 is an integer or not?
Yes.
Obviously, they'll be just negative of each other, no? And negativity does not break the rule of symmetricity, right? This is the symbol for belongs to, right? So we are saying that x minus y holds for the rule, means that x minus y belongs to an integer. If x minus y belongs to an integer, it implies that minus times of x minus y is also an integer, no? If we multiply this thing by negative, that doesn't change when its nature. It will be an integer only. If the value was 4 before, we are multiplying it with minus, so it becomes minus 4. And if minus times of x minus y is also an integer, then we can say that y minus x is an integer, basically. Now for transitivity, consider two condition true first. So if x comma y and y comma z holds for the given rule, then does x comma z holds or not? We have to check this. So we are saying that if x comma y holds, it means that we are saying x minus y is an integer, right? And if y comma z holds, then we are saying that y minus z is also an integer. So let's say x minus y is 5 and y minus z is 7, right? If I add both of them, 5 and 7, then I'll get an integer only, 12. If we add two integers, subtract two integers, or multiply or two integers, then we will get an integer only. It is, I mean, for division, it is not true always, but for addition, subtraction, and multiplication, it is always true that if you are using two integers or more than two integers, but if you are using all the values as integers or all the integral values, then whatever you do, either addition, subtraction, or multiplication, you will get an integer only. So if I add both of them, it will be an integer because they both are integers. Now, by adding both of them, what I'm saying is, this y gets cancelled out. So if I add them, I get x minus z, and that should also be an integer. And see, if we are saying that x comma z, then we are already saying it follows x comma z. Because if x comma z holds, it means that x minus z should be an integer. Right? So if x comma y holds, that is if x minus y is an integer, and y comma z also holds, that is y minus z is also an integer, then x comma z holds or not? And now x comma z holds or not mane x minus z should be an integer. And I got the expression x minus z by just adding both of them. If I add both of them and they also are integral values, then I'm getting an integer only. That is why the given relation is reflexive
Equivalent rate.
equivalence. Yes. Now we have seen the first equivalence relation, I guess. I mean, we have
Sir,
seen the equivalence relation, I guess, but we haven't discussed about this. Yes, please.
sir, if like they're given the relation and we can form, so we don't need to do like this.
Yes,
We are proving here, so they
we
can.
need to do actually like this, what I am doing right now. I mean, if we can do, this is a better method than we were using first. But that was to make you understand what is going through. You have to understand it like that only. But now we are leveling up. You can take it like that. And by first understanding this with some roster forms, with some easy examples, now we are trying to solve some harder problems and also using the concept of these types. Now see, these are still easy questions. The tougher questions will start. Let's solve some first before that, let's solve some of the questions. There's a question, good question in your example. I have to check it. Which one is that? Yeah, these 2-3 questions are really good. Let's come to example 2. Let T be the set of all triangles in a plane, right? T, T is a set which consists all triangles. Now, how many triangles? Infinite, obviously. But it consists of all the triangles which can be possibly made on 2D, which I can possibly draw on this board for you.
Sir, which example?
Example 2, page number 3.
Sir, can you just scroll up?
Yeah. Just first write it and then tell me. Or rather, I should write the question by then.
Yes, sir, finished.
Okay. So T is your set of all triangles in a plane with R relation, with R a relation in T. So we are forming a relation R on this set T. Now set T consists what? All triangles. So we are using triangles for our relation. Triangles are different triangles are basically an element of the set. So there are infinite triangles possible. Now what we are saying is that a relation R in this set T is formed, and the relation has this rule that T1, T2, T1, T2 is a part of the relation if they satisfy T1 is congruent to T2. That is, two triangles which are congruent to each other will be a part of this relation, right? We have to show that R is an equivalence relation. Show that R is an equivalence relation. Now, to start with, first, let's check reflexivity. Reflexivity says that replace T2 with T1 only. Make both of the variables same, right? First we were using x comma y, then we have to replace y with x. Now we are using T1, T2. It's okay. We are just using the different variables, but the concept of the variable is same only, right? So we have to replace T2 with T1, and we have to think about whether T1 is congruent with T1. T1 is congruent to T2. Yeah. So let's start answering now. So is it reflexive or not? If T1 is a triangle and T1 is another triangle, basically we want to know whether a triangle is congruent to itself or not. T1 is congruent to T1 mane what? By if you are replacing T2 with T1, then you are basically comparing what? The T1 is congruent to T1, that the same triangle is congruent to itself, which is true. Every triangle is congruent to itself. You remember congruent, right? Yes, correct. Yeah, please check for symmetricity now. Since it is reflexive. Now symmetricity says that T1, T2 is true. That is T1 is congruent to T1. Now we have to check whether T2 comma T1 will be true or not. Don't take the help from book. I mean, you can solve this easily. I know some of you can face the problem, but still, if you will try to solve it yourself, then only you will get whatever I'm saying. हाँ जी, तो है सिमेट्रिक के नहीं? If for symmetric you have to, हाँ शाविज क्या है? Yes or no?
Yes, sir, it's symmetric.
Yes, it is symmetric. If T1 comma T2 is satisfying the rule, so you have to T1 comma T2. You are saying that T1 comma T2 belongs to R, right? If T1 comma T2 belongs to R, what does it mean? It means that T1 is congruent to T2, right? If T1 is congruent to T2, obviously T2 is also congruent to T1. No? You write it like this or you write it like this. You take T1 first or you take T2 first. It doesn't change the things. And if you're writing T1 is congruent to T2, which also implies that T2 is congruent to T1, it means that T2 comma T1 is also a part of it. Right? If T1, T2 is a part of the relation, then T2, T1 is also a part of the relation. Yeah. So T1 comma T2 belongs to R, then T2 comma T1 also belongs to R. Austin, did you get it? Yeah, Austin, did you get it? Oh. And what about Humamuddin?
Yes, sir.
Okay. Now solve for transitive. Transitive says that T1, T2 as well as T2, T3. Take some other triangle also. If T1, T2 is there and T2, T3 is also there, then you need to prove that T1, T3 is also there.
T1 and T3 are congruent.
Yeah, right. T1 and T3 are congruent. So if T1, T2 and T2, T3 are present in the relation, it means that what? T1 is congruent to T2 and T2 is also congruent to T3. If T1 is congruent to T2 and T2 is congruent to some other triangle, then T1 must be congruent to that triangle. No? And which means what? That T1, T2 also belongs to the given relation. And the relation is reflexive, symmetric, as well as transitive. Hence the relation R is equivalence relation. Now let's try to solve example 3. I'm actually okay. Please write it. Once you're done, is everybody done?
No, sir.
Okay. So I'm writing the next question here. Example 3 भी है इसमें, and there is one more question I will be adding to this example. Austin, are you there in the class?
Yes, sir.
Okay. Did you get it? How did we prove symmetric and transitivity for the last question?
Yes, sir.
Okay. So L is our set of all lines in a plane. And then we are forming two relations on this set L. First is whatever written in example 3, that the relation R satisfies L1, L2, in which what? L1 is perpendicular to L2. So if two lines are perpendicular, they are a part of this given relation. If L1 is perpendicular to L2, then L1, L2 is a part of this relation. Now you have to check whether the relation is symmetric, transitive, or reflexive or not. And then I'll give you another question. Give me 2 minutes. You have 2 minutes. Please try to solve the question. Shahid, the answer is correct. Very good. But did you really understand the transitive part? I'm just curious. Okay. Okay, so let's check for the reflexivity first. For reflexive, L1 is perpendicular to L1. Is it true?
No, sir. It's
No,
not a
right? Yeah. So not reflexive. Can we solve them directly now? No, you don't need to write so much. But we do have to write in the exam. Can't. You have to show it that L1 is not perpendicular to L1. A line is not perpendicular to itself. You have to write it like that. Okay, symmetricity. L1 is perpendicular to L2 is true. You have been given that L1 comma L2 belongs to R. It means that L1 is perpendicular to L2. And this is given as a true statement. Now you have to check for L2 comma L1. Mane L2 is perpendicular to L1. So if L1 is perpendicular to L2, isn't L2 is also perpendicular to L1? Yes, right?
Yes, yes.
So the given relation is also reflexive. Now let's check it like that. अब और थोड़ा direct करते हैं. Let's make it quick. So we have to check for what transitivity now. So transitivity says that L1, L2 and L2, L3 should be there. L1, L2 is there, mane L1 is perpendicular to L2. If L2 and L3 are there, mane L2 is perpendicular to L3, right? So L1 is perpendicular to L2. This is a sign of perpendicular. And L2 is perpendicular to L3, some other line. Let's take it like this. This is a line L1. This is a line L2. They are both perpendicular to each other. Now we have to draw third line which is perpendicular to L2. So anything that is perpendicular to L2 has to be parallel with L1, no? Because L1 is already perpendicular to L2. So if you take two pairs, L1, L2 and L2, L3, then if both of them satisfy the condition, it means that L1 and L3 has to be parallel. And we have to check whether L1 and L3 are perpendicular or not transitive. Why? Because L1, L3 does not belong to this. L1 and L3 will be parallel rather than perpendicular. Okay, second question is, the relation R says L1, L2 is a part of the relation if L1 is parallel to L2. Now let's solve this. Anji, start answering. Reflexive. Every line is parallel to itself. L1 is parallel to L1. Yes. No. Guys, every line is parallel to itself. Hence, the given relation is reflexive. Definitely reflexive. Reflexive. Now, check for symmetricity and transitivity. Correct, Austin. Yeah, if we check for symmetricity, if L1 is parallel to L2, then L2 is also parallel to L1. If L1 is parallel to L2, then L2 is also parallel to L1. Hence, if L1, L2 is a part of the relation, then L2, L1 is definitely a part of the relation.
Sir, in the first part, L1 is coinciding with L1, right? How is it parallel?
Yeah. I mean, they are coinciding, but that is also a condition of parallelism only.
Okay.
So it is reflexive, it is symmetric, and now come to transitive. If L1 is parallel to L2 and L2 is parallel to another line L3, then L1 and L3 are also parallel. Right? If L1 is parallel to L2, what do we say in हम अगर ट्रांजिटिव चेक करना चाहते हैं तो क्या बोलते हैं L1 L2 भी हमारा पार्ट है और L2 L3 भी हमारा पार्ट है हम ये बोलेंगे पहले हम दो पेयर बोलेंगे ये हमारे ऑलरेडी एक रिलेशन का पार्ट है तब हम चेक करेंगे क्या L1 L3 भी पार्ट होंगे कि नहीं सो starting from L1 L2 if L1 L2 is there तो L1 is parallel to L2 now if L2 L3 is there it means that L2 is parallel to L3 यार आप ड्रॉ करके देख सकते हो वैसे एक ये दोनों अगर पैरेलल है और इसके कोई अब आपको ये L1 है लेट्स से दिस इज L2 नाउ यू हैव टू ड्रॉ अनदर पैरेलल लाइन टू L2 देन व्हाटएवर दिस लाइन इज वो हमेशा L1 के साथ तो पैरेलल ही होगी क्योंकि L1 खुद पैरेलल है L2 के तो L2 के भी जो अब पैरेलल है वो L1 के तो पैरेलल हो गई है ना तो गिवन रिलेशन इज इक्विवेलेंस equivalent relation. No, sorry, not equivalent, equivalence only. Right. Now, after this, let's solve 2-3 more questions from the book only, but these are good questions. Okay. Let's solve question number 2 from exercise 1.1, question number 2 and question number 5. Question number 2 says, show that the relation R in the set of real numbers. No, we are given this R set of real number. This is also a standard set. N, R, Z, right? These are standard sets. N is for natural numbers, W is for whole numbers, and R is for set of real numbers. Now you can take any value from minus infinity to plus infinity. right? So all real numbers and we are forming a relation on this set R, which is another, let's name this relation as R1. And now R1 says A comma B is a pair of R1 if A is less than equal to B square. You have to check whether the given relation R1 is your reflexive, symmetric, or transitive in nature. And A and B can be any real value. So reflexivity के लिए क्या करना है? Change B with A less than equal to A square. A less than equal to A square. That will be the condition for reflexivity. Now consider it like this. कि एक number है, A is any number and that is less than equal to its square. क्या ये हमेशा हर नंबर के लिए ट्रू है कि वो अपने स्क्वायर से छोटा ही होगा या उसके बराबर होगा?
No, sir.
The answer is yes. No. When?
Select for 2 square, it will be 4, so it is not.
तो 2 का स्क्वायर 4 है तो 2 से छोटा ही है ना, मतलब सॉरी 2 तो उससे छोटा ही है ना. Every number is smaller than its square or not?
Yes.
समझ आई कि मैं क्या बोल रहा हूँ शायद तेरे को बात? मतलब हम तो यही चेक करना चाहते हैं ना, वो सिंपल, that if a number A is given, then for reflexivity we want to check whether A, yeah, number can be anything. Yes, Austin, number can be anything. So number can be any real number, but we want to check whether the square of every, I mean, whether the number is always smaller than or equal to its square or not. Is there a case where a number is, you are giving me the answer, Austin, or you have written something? Okay, yeah, right. So the answer should be what?
Fractions.
Not reflexive, right?
Yes, sir.
I mean, for reflexivity, it should not, it is not following the reflexivity condition. Yeah, right. Chavez, did you understand it? अभी तक तो हमने आंसर पे बात नहीं करी है, बट हम पूछ रहे थे कि हमें बस कंडीशन ये चेक करनी है. सबसे पहले तो कंडीशन समझना इंपॉर्टेंट है. ऑस्टिन, यू कैन गो टू सिमेट्रिक पार्ट एंड ट्रांजिटिव पार्ट.
Yes.
तो हमें बस ये कंडीशन समझना जरूरी है कि हम कर क्या रहे हैं. तो हर नंबर अपने स्क्वायर से छोटा है कि नहीं ये चेक करना चाहते हैं. अब आप सोच के बताओ मेरे को कि क्या ये ट्रू है हमेशा या नहीं? फायजा, हमामुद्दीन, शाहिद एंड शाविज.
Yes, sir.
अच्छा, तो कैसे, हाउ डिड यू नो ये ट्रू है? यू टुक सम एग्जांपल्स, है ना?
Yes, sir. 1, it's equal.
है ना? तो हम यही करते हैं कि हम एग्जांपल लेंगे कुछ कुछ, तो ऐसे यही प्रोसीजर होता है क्वेश्चन सॉल्व करने का. पहले तो ये समझ लो. देखो, दिस इज द प्रोसीजर हाउ वी प्रोसीड. वी टेक some examples out of the given set, we try the rule on them. We don't check it for every value. अभी set है real numbers का, है ना? तो I have infinite numbers, I can't check it for every value, right? तो what I will do, I will try to find one pair or one value जहां पे false हो जाए. मेरे को इसके false case, मतलब मेरे को इसके fail cases देखने हैं. फेल केसेस अगर एक भी मिल गया कि नहीं भाई, एक नंबर तो है मेरे पास जिसका स्क्वायर जो अपने स्क्वायर से बड़ा है, तो मैं बोल दूंगा कि ये रिफ्लेक्सिव नहीं है. राइट? वी जस्ट वांट वन पेयर. करेक्ट, गुड. गुड, एकदम शायद यही करना है अपन को। जब भी हम नो आंसर देंगे ना किसी भी चीज का, तो वी विल शो अ फेल्ड केस।
Yes, sir,
वी
it's
विल,
not.
या, हाँ बिल्कुल बिल्कुल, इट्स नॉट रिफ्लेक्सिव। व्हाई शाविज?
Yes, sir,
मेरे को एक
like
फेल्ड केस दे दे।
1/2 square, we are getting 1/4.
बिल्कुल, if we take 1/2 as a, then 1/2 square is 1/4. In fact, all the numbers between 0 and 1 are like that. Higher the power, the smaller will be the number. If you take any number from 0 to 1, and if you take its powers, let's take 1/2. So higher the power, smaller the number. If you take power 2, 1/4. If you take power 3, 1/8. Power 4, 1/16. Right? So as when the number is in between 0 to 1, then its higher powers are smaller in nature. This is only applicable for the numbers between 0 and 1. I mean, obviously from -1 to 0 also, but they are already negative. Right? So now to take your, अब शाविज यार ये तो गलती हो जाएगी। प्रॉब्लम ये है कि इसको ऐसे समझने का है कि हमेशा हमें तो नहीं पता चलेगा कि ये बात सच है कि नहीं है। अब इतने देयर आर इनफाइनाइट केसेस, वी कांट ऑब्वियसली सॉल्व, we can't obviously write R1, you know, in this case. So what we will have to do is we will have to take examples. Now, how do we take examples? Because it is very common that you can leave some example which was false for this case. You know? So to take the better examples, always divide your real number, that is -infinity to +infinity, into 4 parts. You have to take one example from each part for the better understanding. Okay, so let's divide it into first 2 category, negative and positive. Then positive may be 0 to 1, there is another category, and negative may -1 to 0. So now there are 4 parts. One part is -infinity to -1, another part is -1 to 0, then third part is 0 to 1, and fourth part is 1 to infinity. So if you divide your whole real numbers into these 4 parts and you take examples from, you take values from each part, then most probably you will be 99% of the time you will be correct. I'm not saying every time, but 99% of the time you will be correct if you take examples from all these parts. So always divide your whole number line into 4 parts. Now, why did I divide it like that? Because they follow the same nature. So all the numbers from -infinity to -1 are similar in nature. वो सब एक तरीके से ही चलेगा. Powers, you take about powers, you talk about different operations, whatever operations you are applying, mathematical operations, those all the operations usually work in a similar way in these 4 categories, all the numbers in each category. So if you take any number from -infinity to -1 and you take another number from -infinity to -1, most probably they will be showing the same result. Same result माने जैसे यहाँ पे अगर हम बात करें तो if you take -2 is smaller than -2 का square, right? Similarly, -5 will also be smaller than -5 का square, right? तो दिस वर्क्स लाइक दैट. अगर आप इन चारों से एग्जांपल उठाओगे तो मोस्ट प्रोबेबली आपका आंसर हमेशा करेक्ट रहेगा. तो व्हेनेवर यू वांट टू टेक एनी एग्जांपल, इंक्लूड ऑल द 4 केसेस. ठीक है. नाउ इफ यू वुड हैव इंक्लूडेड दिस, तो यू विल गेट टू नो दैट द गिवन कंडीशन इज फेल्ड इन दिस केस 0 to 1. और इसके अलावा यार वी कैन सॉल्व इट बाय नंबर लाइन रूल. दैट्स अ मैथमेटिकल मेथड. मतलब we do have this to solve, we can solve it. I don't know how many of you know about this or not, but you should, at least 2-3 guys should. Shahid, Chavez, and Austin, I guess. I don't know, Austin, whether you are preparing for any competitive exam or not. Are you?
For need, sir.
No. Yes.
No, sir. I meant only for need.
Okay. In that case, Shahid and Chavez, you both should know this method, what I'm telling you. I'm not telling you the method because we will be studying about it in increasing and decreasing functions, chapter 6. So we'll be discussing this there, but I just want to tell you that we could have solved it like that. A less than equal to a square. So okay, I'm going to write it completely because I'll be needing we will anyway have to solve the question. So we are checking out for reflexive condition first. So for reflexive, now we could have approached in two ways. For reflexive, replace B with A, right? Then the relation condition becomes A less than equal to A square. Or we could have written directly like this, that for reflexive, A should be less than equal to A square A should be less than equal to A square for all A belongs to R. That is, for all real numbers, this condition must satisfy. If we want this relation to be reflexive, this condition that A is less than equal to A square should be satisfied for all the real numbers, right? Now, in this case, either I can show this like this, that A minus A square less than equal to 0. Rather than this, write it like this. Take A to the right hand side. Then this is A square, this becomes minus A. Now A square minus A greater than equal to 0. You can take A common. So you got A into A minus 1 as the factors. You find out zeros of these factors. So the root of these factors. So A minus 1 ka root hoga 1. Or the root of A is 0, right? Root is wherever this expression is getting 0, right? We do know about root. So we'll plot these roots 0, 1, and we will use number line or sign rule method, which says that all the numbers from 1 to infinity, this condition is positive. And for all the conditions, all the numbers from minus infinity to 0, this condition holds. But all the numbers from 0 to 1, उसके लिए ये condition hold नहीं करेगा. So all the numbers from 0 to 1 are not following the given condition because there is a negative there. Now, how are we assigning these signs? That we will be discussing later on. But we could have solved this easily like that. अगर हम ऐसे mathematically बात करें तो यहाँ से भी हम बोल सकते थे. We could have easily solved it like that, and then we could have tell that A belongs to 0 for A. Rather, we should write it like that. For A belongs to 0 to 1, the given condition does not hold. One way to solve is like this. Or another way is just take one example where the case fails. But for that, you will have to consider all four parts. So, but for A is equals to half, if you put A is equals to half, then half is not less than equal to money, you can cut this symbol 1 by 2 square. 1 by 2 square, which is basically what? 1 by 4. So 1 by 2 is not less than equal to 1 by 4. So for A half, for the value of A as half, this condition does not hold, hence not reflexive. Because we found one value where the given condition does not hold. Now check for the symmetricity. So you start with examples only first. Don't go to this part. ये अभी solve नहीं होगा. Just check with some examples whether the given relation is symmetric or not. Symmetric says if A comma B belongs to R, or rather R1, then B comma A should also belong to R1. Now, if A comma B belongs to R1, what does that mean? That A is less than equal to B square, right? We want to know whether B will also be less than equal to A square or not. At first sight, I don't think it is true. We can easily find, in fact, always approach all the questions of reflexivity, symmetricity, and transitivity like this. You should have a doubt that always consider the statement false and try to find out a single pair where it is false. मतलब solve तभी कर पाओगे जब ऐसे सोचोगे. मैं नहीं कह रहा कि हमेशा false होगा. I'm not saying that every time the statement is false. I'm just saying that you have to think like that so that you can find that pair. क्योंकि देखो एक भी मिल गया false case या sorry failed case तो काम हो जाएगा अपना. So you just have to find one failed case, and to find out that failed case, consider the statement in your hand as positive, as false, and then try to find out that case. तो एक एक एग्जाम्पल देके बता सकते हो. यू कैन जस्ट गिव मी एन एग्जाम्पल. कहां पे फेल हो रहा है सिमेट्रिक के लिए? क्या है कोई एग्जाम्पल ऐसा? शाहिद ने बता दिया आंसर. लो ना, मतलब मुझे क्या प्रूव करना है, मुझे क्या फेल करना है? मेरे को फेल ये करना है कि बी ए स्क्वायर से बड़ा हो, है ना? मतलब बी ए स्क्वायर से, मतलब मेरे को एक ऐसे दो नंबर चाहिए जिसमें पहली बार तो फर्स्ट नंबर सेकंड नंबर के स्क्वायर से छोटा हो. जैसे फॉर एग्जांपल 1,2, तो 1 2 के स्क्वायर से छोटा है ना? अब क्या 2 1 के स्क्वायर से छोटा है? नहीं. तो हो गया ना एग्जांपल 1,2. टेक योर ए एज 1 एंड बी एज 2. अब मैं कहना क्या चाहता था, मैं तो ये कहना चाह रहा था कि बी को बड़े से बड़ा नंबर लो, ए को छोटे से छोटा नंबर लो, तो कंडीशन तो ये सेटिस्फाई हो ही जाएगी फिर इन दैट केस भी. आप बी को बड़ा नंबर लोगे, ए को छोटा नंबर लोगे, तो ए लेस देन इक्वल टू बी स्क्वायर वाली कंडीशन तो सेटिस्फाई वैसे ही हो रही है क्योंकि ए बी से ऑलरेडी छोटा है. बट बी स्क्वायर करोगे तो और भी छोटा ही हो जाएगा, है ना? तो कोशिश करो कि बी को बड़े से बड़ा नंबर लो, ए को छोटे से छोटा नंबर लो. मतलब छोटे से छोटा से माने मतलब छोटा, कोई ऐसा नहीं कि माइनस इन्फिनिटी लेके बैठ गए. तो मतलब मैं कहना ये चाहता हूँ कि छोटा नंबर लो थोड़ा. तो ए को 1 लिया, बी को मैं बहुत सारी वैल्यूज ले सकता हूँ, लेट्स से 10 भी ले सकता हूँ. तो बी को 10 लूंगा तो 1 लेस देन इक्वल टू 100. ट्रू है भाई. बट क्या 10 1 के स्क्वायर से छोटा है? नहीं. सो टेक a इज इक्वल्स टू 1 एंड b इज इक्वल्स टू 2. तो 1 इज लेस देन इक्वल टू 2 स्क्वायर. बट 2 is not less than equal to 1 square. It implies that the given relation is not symmetric. बस एक एग्जाम्पल हमें ऐसा मिल जाए which is supporting our condition. अब ट्रांजिटिव वाले में थोड़ा प्रॉब्लम होगा. तो देखो ट्रांजिटिव के लिए पहले तो ये समझ लो एबीसी कैसे चूज करने. फर्स्ट स्टेप शुड बी दिस. ए शुड बी द मिनिमम. नो भाई, मैं प्रूव क्या करना चाहता हूं? ए बी बी सी अगर R1 का हिस्सा है तो ए कॉमा सी भी R1 का पार्ट होगा. दैट इज व्हाट आई वांट टू प्रूव, राइट? अब ए लेस देन इक्वल टू बी स्क्वायर है, बी लेस देन इक्वल टू सी स्क्वायर है. ये हमें गिवन है ऑलरेडी, क्योंकि ए कोमा बी और बी कोमा सी तो आप मान के चलते हो ना कि हमारे ट्रांजिटिव का पार्ट है. तब हम चेक करते हैं कि ए कोमा सी पार्ट है या नहीं, है ना। सॉरी, अभी हम देखेंगे कि क्या कैसी वैल्यूज हमें लेनी चाहिए, राइट। वी वांट टू प्रूव इट रॉन्ग, प्रूव इट फॉल्स। ठीक है, तो ए यहां पे बी स्क्वायर से छोटा है और बी सी स्क्वायर से छोटा है। मैं चाहता हूं ए सी स्क्वायर से छोटा ना हो। अगर ए सी स्क्वायर से छोटा नहीं होगा, एक भी केस ऐसा मिल जाता है, तो इन दैट केस मैं ये भी बोल सकता हूं कि द गिवन रिलेशन इज नॉट ट्रांजिटिव। तो ए यहां पे बड़े से बड़ा लो। भाई आप तो फॉल्स प्रूव करना चाह रहे हो ना। पिछले केस में आपका पर्पस था फॉल्स ही प्रूव करना था, बट सिमेट्रिक के लिए था सिर्फ। तो वहां पे ए छोटे से छोटा लिया, बी बड़े से बड़ा लिया, जिससे कि पहली कंडीशन सेटिस्फाई हो जाए बट दूसरी में प्रॉब्लम आए, तभी प्रॉब्लम आती। अभी यहां पे अगर मैं बात करता हूं तो मुझे ऑलरेडी पता है कि ए लेस देन इक्वल टू बी स्क्वायर है, बी लेस देन इक्वल टू सी स्क्वायर है। मैं चाहता हूं ए लेस देन इक्वल टू सी स्क्वायर है कि नहीं ये पता करना, राइट। अगर ए लेस देन इक्वल टू सी स्क्वायर है तो ट्रांजिटिव हो जाएगा, नहीं है तो नहीं होगा ट्रांजिटिव। पर मैंने पहले ही क्या बोला कि मैं तो मान के चलूंगा नहीं है, नहीं है, ठीक है जी। नहीं है तो कैसे, अब कैसे नहीं है तो क्या होगा, तो ए बड़ा होना चाहिए फिर सी स्क्वायर से। ओके, अब तुम कह रहे हो ए बड़ा है सी स्क्वायर से, व्हाट डज इट मीन, दैट ए नंबर ही बड़ा होना चाहिए, राइट। बड़े से बड़ा नंबर लो फिर तो इसको। तो चलो अब कुछ कंडीशन लेते हैं ऐसी जहां पे हमारा ये हमेशा सेटिस्फाई हो रहा हो, राइट। ओके, so let's take a as what, 8. Okay, let's take b as 3, क्योंकि 3 का स्क्वायर 9 हो जाएगा। Now b is 3, take any c जिसका स्क्वायर 3 b से बड़ा हो जाए। तो या तो मैं c को 2 ले सकता हूं, या मैं c को √3 भी ले सकता हूं, नहीं क्या। अगर c को ही मैं √3 ले लूं तो √3 का स्क्वायर 3 हो जाएगा और b के बराबर भी आ जाएगा, तो कंडीशन तो सेटिस्फाई हो जाएगी। बट चलो मैं b को c को थोड़ी देर के लिए 2 ले लेता हूं। कुछ भी ले सकता था, मैं ये दिखाना चाह रहा हूं बस। बहुत सारे तरीके हैं, हम ये नहीं कह रहे कि एक ही तरीका है, यही फेल्ड केस है, बहुत सारे फेल्ड केस होंगे। हमें तो एक चाहिए अपना पॉइंट प्रूव करने के लिए। तो चलिए जी, सी को 2 ले लिया, a 8, b is 3 and c is 2. Now if I consider, तो 8 is less than equal to 9 करेक्ट है, 3 is less than equal to 4 करेक्ट है, बट क्या a which is 8 is less than equal to c square which is 4? No, right? So मैं यहाँ पे बता सकता हूँ a is equals to 8, b is equals to 3 and c is equals to 2. Transitive condition does not hold. Right? तो बोल सकते हैं neither the given, I mean the given relation is neither not reflexive, not symmetric and not transitive as well. समझ आई आप सभी लोगों को ये बात, किस तरीके से हमें चेक करने टाइप्स ऑफ रिलेशंस।